Hi everyone, this is the beginning of our fourth unit. This is going to start with section 6.1, characteristics of higher order polynomials. The objectives in this section are to identify the graphs of higher order polynomials, graph cubic and quartic polynomials, and then find local and absolute min and max values of polynomial functions. So we've already recently done quadratics, which are a type of polynomial. Those are a degree 2 polynomial because the highest exponent we saw with those was a 2. So now we're going to see what happens if our powers start to get higher. So we're going to start by first formally defining a polynomial function. A polynomial function of degree n is a function of the following form. And we'll kind of break it down with some numbers here, but pretty much this is a coefficient times a variable to a power, plus or minus a coefficient times a variable to a power. And notice our powers are n minus 1, and then it goes to essentially a 1 and a 0. We say these coefficients are in descending order. There's some conditions. N, meaning our powers, need to be non-negative integers. So our whole numbers, 0, 1, 2, 3, 4. So no negative exponents, no fraction exponents, no decimals, anything like that. Our coefficients are going to be real numbers, and our leading coefficient, which we'll define officially in a second, cannot equal 0. So let me give you an example of a polynomial. It would look something like this. G of x equals 5x to the 7th minus 4x to the 5th plus 2x squared minus 3x plus 1. So this is an example of a polynomial in with its terms in descending order. So again, those are my exponents arranged highest to lowest, kind of like what we were doing with our quadratics. We always put the highest power first. We're going to use this polynomial to define some other common terminology that you're going to see with polynomials. The first one is called the leading term. The leading term of the polynomial is a sub n x n, which you will see in our original definition up here is really just the whole first term. So in my polynomial, the leading term would be 5x to the 7th. If your terms were not in order, you would make sure to order them first before you name that leading term. Then we have in that leading term what we call a leading coefficient. That's a sub n. So it's just the number out front, 5. And then we have a constant. Sometimes you have a constant, sometimes you don't. The constant term is a sub 0, which again, if you go back to our original definition, that's the term that does not have a variable. So our constant here is, not 0. Thinking something else, sorry. It's 1. It's the number that does not have a variable. There we go. Then we have a couple special cases of polynomials. The first is the constant function. The constant function is f of x equals a, or essentially y equals a number. So we've seen those before. Those are our horizontal lines. Like an example of a constant function would be f of x equals 7. This is a polynomial of degree 0, and we say it's degree 0 because at the end of it we can always put an x to the 0 power. Remember from our exponent rules, anything to the 0 power is equal to 1, so that's not changing what my function is equal to. And then because that is my highest exponent or my only exponent, we say it's the degree. Now speaking of degree, let's go back to our original polynomial. Part of the definition said this polynomial is degree n. So whatever the highest exponent is, which should be the exponent that comes first if your terms are in descending order, is your degree. So if we go back up to my polynomial here, we say the degree is 7, my highest exponent. Or again, my constant function, the degree would be 0. And a line in y equals mx plus b form would be a degree of 1 because the highest exponent is 1. Or a quadratic, which has, remember, an x squared in it, would be a degree of 2. So those are the highest powers that we see. There's also a special case called the 0 function. The 0 function is just y equals 0. That's the only one that we say has no degree assigned to it. There are some special names for polynomials. Like I said, a degree 1 is a linear equation. We've done those. A degree 2 is a quadratic. A degree 0 is constant, all things we've seen. A degree 3 is called a cubic function. A degree 4 is called a quartic function, and those two are what we're going to see mostly in this section. And then another special name is a degree 5 is a quintic polynomial. After that, we just say degree 6, degree 7, degree 8. We don't have really any special names for them. So in addition to having some restrictions on what the equation themselves looks like, properties of polynomials are also listed here that can help you if you're not sure if something is or is not a polynomial. All polynomials will have a domain of all real numbers. And remember, we put that in interval notation before, negative infinity to positive infinity. So that means if you have any domain restrictions, things that would be a variable in the denominator or a square root, things that we know could cause domain restrictions because we can't have a 0 in the denominator or a negative under the square root, then you know that it is not a polynomial. So we should have no issues with our domain if we're looking at a polynomial. In addition, the graph is a continuous and smooth curve. So continuous and smooth curve look like the graph in the middle. The graph in the middle is a polynomial function here. I can trace this whole graph with my pencil without having to pick up my pencil. So the graph on the left, you'll see, is not a continuous curve because we have a gap in the graph. Even though the domain of this would be all real numbers, there's no x values that don't have a y that go with them on this graph. Because we have that gap, we say that it is not continuous, so it is not a polynomial. In addition, smooth curve means if it turns anywhere, and we're going to call those turning points, they are not sharp corners. So the picture on the right here, these sharp corners make it not a polynomial. An example of a graph that we've seen already that has sharp corners is the absolute value function. The absolute value function is a continuous curve. Its domain is all real numbers, but it has a sharp corner at its vertex, so it is not an example of a polynomial. Okay, so in our first few problems here, we're going to determine if these are polynomial functions. If not, we're going to explain why. And if so, we're going to find some of those terms, the degree, the leading term, and the leading coefficient. So remember, to determine if it is or is not a polynomial, one of the biggest things to look for is, are there any domain restrictions, any values that x cannot equal? So if I'm looking at this first one, I have a denominator. X cannot equal 1, because if x equaled 1, 1 minus 1 in the denominator would make my denominator equal to 0. So because I have a domain restriction, it is not a polynomial. I can spell, there we go. In the second one, again thinking about domain restrictions, I have a square root. X can only be numbers that are greater than or equal to 0 here, because I cannot have a negative under that square root. So again, it is not a polynomial. In the third one, we have a negative exponent. Not necessarily bad, but remember what a negative exponent means. If I want to make that exponent positive, I move the variable to the denominator. And now you can see where we would end up with a domain restriction. X cannot equal 0. So it is not a polynomial. In addition, part of the definition of polynomial a couple pages ago said that my n's, my powers, must be non-negative integers. So you could also say it's not a polynomial because you have an exponent that is a negative integer. Let's look at the fourth one. The fourth one has no domain restrictions. There's no denominators, no square roots, no weird exponents that are not non-negative integers. So this is a polynomial. The first thing I'm going to do is reorder these terms. I want my exponents highest to lowest to get it in what we are going to call standard form of a polynomial. So my first term will be negative 7x to the fourth. My second term will be negative 5x. And my last term will be positive 3. So now if I want to say my degree is my first or my highest exponent. They should be the same thing if you've ordered them correctly. So we say this is a degree 4 polynomial, which, remember, there's a special word for those, quartic. If I want the leading term, that's just the first term, negative 7x to the fourth. If I want the leading coefficient, the leading coefficient is the number in front of the leading term, negative 7. And then one thing it didn't ask for up top, but I'm going to add it here, is the constant. The constant is the number that does not have a variable. So here our constant is 3. Okay, let's look at the next one. We have f of x equals 8. So think of it as y equals 8. That's a horizontal line. Remember, that was one of our special cases. So yes, it is a polynomial. The degree of all horizontal lines or constant functions are 0, because remember, you could put an x to the 0 at the end of that. The leading term is 8. That's the only term. The leading coefficient is 8. Again, that's the only coefficient. And the constant is also 8, because it's a number that does not have a variable in its term. Finally, my last one here. Again, I'm looking at my variables. There's no number that my variable cannot equal, no domain restrictions. My exponents, I don't have any non-negative integers. I do have this weird coefficient of pi, but there's nothing in the definition of a polynomial that says you can't have an irrational number as a coefficient. So we say that yes, this is a polynomial. Again, I'm going to reorder my terms first here. So I'm going to rewrite it as f of x equals, the highest exponent is first, pi x to the third. Then my x term would come second. Make sure the negative stays with it. Negative x plus 4 at the end. So now we can say that the degree is 3, and this was a cubic function, remember, was a special name for that. The leading term is pi x to the third. The leading coefficient is pi. And then my constant is 4, the number without a variable. The next thing we're going to talk about are end behavior of polynomials. So we'll get into more graphing these polynomials by hand, but in this lesson we're just going to talk about some basic properties that they have. Because they're continuous graphs on the left and the right, as we go further to the left on the graph and further to the right, these graphs will ultimately either be going up or down forever. And so when we're talking about end behavior, we're talking about the arrows on the graph. What's happening? On the left, is it going up or down? And on the right, is it going up or down? A way to determine an end behavior of a polynomial without looking at its graph is by looking at the degree. So let's say n is the degree of our polynomial and its leading coefficient. And again, a sub n is what they use to represent the leading coefficient. There are 4 different cases, and notice that kind of in the middle here we've got some dashed lines instead of solid lines, because we don't really know what's happening in the middle of the graph right now. Remember, we're only focusing on the ends of the graph, the end behavior. So the first 2 cases are when you have a degree or an n that is even. So that's case 1 and case 2. And I'll write degree even here. On the bottom, those 2 cases are if your degree is odd. Now you'll notice the 2 that are even, the ends are going in the same direction. They're either both up or both down. The odd degree functions are, our ends are going in opposite directions. One's going up and one's going down. To determine if it's case 1 or case 2, or if it's odd, case 3 or case 4, you then look at the leading coefficient. If the leading coefficient is positive, it's either case 1 or case 3. If the leading coefficient is negative, it's case 2 or case 4. And we'll be doing something in a second. We'll like formalize all of that. But right now, we're going to go ahead and list the end behavior of these functions. And there's a very specific way that we do it. The notation looks like the following. We say x approaches, that's what that arrow means, negative infinity, and x approaches positive infinity. So that means we're going to look on the left and we're going to look on the right of each graph. So they're always going to start the same way. I'm going to write that same thing for each of these. X approaches negative infinity, x approaches positive infinity. Your job when you're naming end behavior is to say on the left and on the right, what's the y doing? So remember, y is our height, and there's two possibilities that can happen on the ends. Either the graph is going up or the graph is going down. So if we're looking at case 1, on the left it's going up, and on the right it's going up. So we say that both ends, both y's, approach positive infinity. If we're looking at case 2, both ends go down. So we say that y approaches, on the left and on the right, negative infinity. If we're looking at the odd functions, one is positive and one is negative. In case 3, on the left side, my end is going down. So as x approaches negative infinity, again, that means on the left, my y approaches negative infinity. On the left, it goes down, is what that tells us. As x approaches positive infinity, that means on the right, my y also approaches positive infinity. It goes up. And then finally, case 4, on the left, it goes up. It approaches positive infinity. And on the right, it goes down, approaches negative infinity. So this is going to be a great way to match an equation with a graph or get a graph from an equation. We're going to be using this in various ways, but you're going to need to know these 4 general cases where both sides go up, both sides go down, and then case 3 and 4 where one goes up and one goes down. Whether the coefficient is positive or negative will determine that. To formalize all of that, we call it the leading term test. So the degree and the leading coefficient can both be found in that leading term, that a sub n x to the n, as part of our polynomial definition. So we say that we use the leading term test to determine end behavior, and we're going to do that at the bottom two problems here. So the first thing I need to do for the first function, f of x equals negative x to the 4th plus 3x squared plus 4, is I need to find my leading term. The leading term, as long as your exponents are highest to lowest, is your first term, and it contains, again, your leading coefficient and your degree are the 2 pieces of information that we need. The leading coefficient is the number in front of my variable, and the degree is my power. So more importantly, my leading coefficient here is negative, and my degree is even. So if we look back on the previous page to the 4 cases of end behavior, I want to find the one that the leading coefficient is negative and the degree is even, and that is case 2. So case 2 says, if that's the case, both ends are going to go down, and this is the shape that I would remember. It almost looks like a parabola going down. If you can, from negative and even, picture this shape, you can list the end behavior. Again, it always starts the same way. X approaches negative infinity, x approaches positive infinity, y approaches, y approaches. And because on both ends here, my y's go down, we say my y approaches negative infinity, and there's my end behavior. Okay, in the next one, again, let's do the same thing here. Let's name our leading coefficient and our degree. My leading coefficient is in the number in front of the very first term, as long as my exponents are ordered highest to lowest, so that would be 1 here. My degree is my highest power, 3. More importantly, my leading coefficient is positive, and my degree is odd. So again, you can look back to your 4 different cases here. A positive leading coefficient and an odd degree are case 3. So I would picture what kind of looked like our basic x to the 3rd or cubic graph shape, something like this. Again, we start the same way. X approaches negative infinity, x approaches positive infinity, and we want to say on the left and on the right, what's happening? On the left of this graph, it's going down, so we say y approaches negative infinity. On the right of this graph, it's going up, so we say y approaches positive infinity. Let's use what we know about n behavior to help us find information from these graphs. The instructions here say for each graph, determine if the degree is even or odd and the sign of the leading coefficient. So this is really just the opposite of our leading term test. We're going to use the ends and we're going to work backwards. So if the ends go in the same direction, like the graph on the left here, we know that the degree is even. So this could be a degree 2 or 4 or 6 or 8, and we'll talk about how to know that a little bit more later on, but we know the degree is an even number. And then, because both ends are going up, we can say that the leading coefficient has a sign that is positive. So the number in front of this polynomial will be a positive number. If we look to the graph on the right, again, we're going to focus in on our ends. The ends here are going in opposite directions. So we say that the degree is odd. And in general, if it starts high and ends low from left to right, that means your leading coefficient is negative. If this graph looked the opposite, if it started low and ended up high, then I would say that the leading coefficient is positive. Okay, here are 2 end behavior problems to try on your own. For problem number 1, the leading term test, hopefully I didn't trick you too much here. These are a little out of order. My leading term is negative 3x to the 7th. So our degree here is 7, and our leading coefficient is negative 3. More importantly, your degree is odd, and your leading coefficient is negative. Out of the 4 cases of end behavior, that's the one where it's going down from left to right, and the ends are going in opposite directions. Your end behavior should look like the following. Always starts out the same way. I'm just setting it up. As x approaches negative infinity, that means on the left, this is going up forever, so my y approaches positive infinity. And as x approaches positive infinity, meaning on the right, my y approaches negative infinity. Remember, y is the same thing as our function notation, so sometimes you'll see instead of y approaches, you might see g of x approaches because that was the original function here, but know that those mean the same thing. Okay, number 2, it says for the graph below, determine if the degree is even or odd and the sign of the leading coefficient. So here are ends. You can see one is going down and one is going up. So hopefully you said that the degree, that means, is odd. Also, if we want to know the sign of the leading coefficient, we want to look at, is it going down to up if we look at the graph from left to right, or up to down. In this case, it starts low and it ends high. That means that your leading coefficient is positive. And if you're not sure about those until you really have the 4 cases down, you can always look back to that chart that said degree, even or odd, leading coefficient positive or negative, and figure out which of the 4 cases you're looking at. Or if you have the graph, find which one matches which case, and then use that to work backwards and figure out the degree and the leading coefficient. Okay, the next couple definitions talk about turning points and x-intercepts. X-intercepts, remember another word for those is zeros or roots or solutions. All of those things we're going to see pop up again in this chapter. Most of the time when we're talking about polynomials, we don't use the word x-intercept, we use zero, real zeros. A polynomial function of degree n has at most n real zeros. So that means if I have a degree 5 polynomial, there can be at most 5 zeros or 5 x-intercepts. At most is key here because there could be less. There could be 4 or 3 or 2 or 1, but there will not be any more than the degree. We also have something called a turning point. We've kind of mentioned that before when we did mins and maxes. Turning points are when the graph turns around, like our vertex on our parabola. It changes from decreasing to increasing or increasing to decreasing. So on the graph to the left here, you can see my x-intercepts are labeled, places where it's crossing the x-axis. Remember, those are also zeros. And then turning points are anywhere where the graph is turning around in its direction. A theorem that goes along with turning points is, again, if we have a degree n polynomial, that we have at most n minus 1 turning points. So that means, for example, if I have a degree 5 polynomial, I could have at most 4 turning points, or it could be less, 3 or 2 or 1 or none. All right, so let's look at the problems on the bottom here. I want to find how many turning points there are and any real zeros of the function. I'm going to start with zeros. Zeros are just x-intercepts, and you should be able to name those from the graph. It's where it's crossing the x-axis. So this first picture is crossing my x-axis at -3, -1, and then it also touches the x-axis at 2. So we say we have those real zeros. If I want to name turning points, or in this case we don't even have to name them, we just need to find how many there are, we're just going to look for any place where the graph is turning around in direction. So we would have a point here that would be a turning point, here that would be a turning point, and here that would be a turning point. 1 looks like, or -1 looks like it flattens out a little bit, but it doesn't turn around in any direction. It doesn't go from increasing to decreasing or decreasing to increasing. So we say we have 3 turning points. In the problem to the right, again, I'm looking for x-intercepts or zeros first. My zeros are anywhere where it crosses the x-axis, and we would just have one of those approximately, I would say it may be like 2.5. Okay, we don't know any more than that without having an equation. Then I want to find the number of turning points. The number of turning points are how many times this graph changes direction. So if I'm counting them up, I have 1, 2, 3, 4 places where it's turning direction. The next thing we need to talk about is multiplicity of zeros. If a number is a zero of a polynomial function, and we're going to talk about that, has to do with factors and solving. We did a little bit of that with quadratics, and we'll get more into that as this chapter continues. A factor or a zero can occur, and we're just going to focus on the zero part of it right now. A zero can occur a certain number of times in the polynomial as we're solving. That said, we say that that zero, whatever it is, has a multiplicity of m. Okay, so a zero at 3 might occur 5 times. So we say 3 has a multiplicity of 5. And we'll see that in equations later on. What's important about the graph of a polynomial is if the multiplicity of a zero is odd, the polynomial will cross through the x-axis at that point. So if I have a, ignore my bell. If I have a x-intercept or a zero that has a multiplicity of 3, so it would occur 3 times in my equation, and again, we'll see the equation part of this later on, then I know at 3, it occurs, it goes through the axes, okay? If I have an even multiplicity, we say the graph touches, or sometimes we'll use the word turn around on the x-axis. So for example, if I have a zero that occurs 4 times, that means wherever that zero is located at, it would touch the x-axis and turn around. And it might be going down till it gets to that point, so then it might bounce back up, or it might be going up to get to that point and it might bounce back down. But it does not go all the way through the x-axis. So what's important to remember is multiplicity, whether it's even or odd, tells us what's happening at that zero. Is the polynomial crossing, or is the polynomial turning around or bouncing off of the x-axis? And that's going to help us get sketches that we're going to do on the next page here. So let's say I want to have a degree of 5 polynomial. I want it to have a negative leading coefficient, and I want to have 3 x-intercepts. Degree of 5 and negative leading coefficient tell me about the end behavior. So if it's an odd degree, we know that my ends are going to go in opposite directions. And if we have a negative leading coefficient, I know it's going to be going down from left to right, something like this. That was one of our cases. So as far as we're concerned, again, this is just a sketch, so we don't have any real specific numbers here. I just know on the left, this graph's going to go up, and on the right, this graph is going to go down. I also know that there need to be only 3 x-intercepts, meaning 3 places where it crosses the x-axis. And I'm just making up numbers right now. It can be any place where it crosses the x-axis, but only 3 of them. So now to make a sketch of the polynomial, we want to connect the dots from left to right. And remember, this needs to be a smooth curve. So we need to figure out how we can cross through these to get from one to the other. Remember, you can also bounce off. So I could do something like this. Maybe I'll cross here, and here would be the issue now. If I cross here, I won't be able to get back down without having an extra x-intercept. So I need to make sure I do something like this maybe instead. I bounce through, and that ensures there's only 3 places where it's crossing. Now, if I look at this graph and I wanted to know about multiplicity, how many times these zeros are occurring, anywhere where it bounces is a multiplicity that is even. So there and there. And anywhere where it crosses through is a multiplicity that is odd. Okay, now this is absolutely not the only way to graph this. This is just a rough sketch that has these properties. So let's look at another one. The next one is a degree 3 polynomial. So again, it's odd, with a positive leading coefficient. So that would be the opposite of our last problem. Ends going in opposite directions, but now it's increasing from left to right. So that tells me on the left, this graph is going to go down, and on the right, this graph is going to go up. Between those ends, I need to have 3 x-intercepts. So maybe I'll do here, here, and here. Again, it can be anywhere. Right now, we don't have any more specific information than that. I need to connect these in a way that ensures that I can get from one to the other here. So I need to go 1, 2, 3, something like that would work. And that would ensure that I have a degree 3 polynomial with 3 x-intercepts. Each of these x-intercepts are odd, multiplicity odd, which means they each occur 1 time because I have a degree 3 polynomial. And remember, we can't have any more zeros than our degree. Okay. Degree 4 polynomial with a positive leading coefficient and 2 x-intercepts. So if it's a degree 4, my degree is even. Positive leading coefficient tells me my ends are going to look something like this, both of them going up. Okay. One thing I want to tell you is if you notice these multiplicities, they're going to start adding up to our degree. So even, let's pick the lowest even number we know, 2. Odd, 1. Even, 2. 2 plus 1 plus 2 gives me a degree 5. These were all odd, 1. 1 plus 1 plus 1 gives me 3. So we need to look at our zeros and their multiplicity and make sure they add up to 4 here at the end. So I want a positive leading coefficient, and I want 2 x-intercepts, maybe here and here. Well, if I want all of my multiplicities to add up to 4 total, that means each of them would have a multiplicity of 2, meaning they need to be even, which means I need to bounce off of those x-intercepts. So again, multiplicity that's even, something like 2, multiplicity even, again, 2 would work here. Again, I'm just making some rough sketches here. You guys are ultimately going to be matching these really when you're doing my math lab because there's so many variables that come into these with the numbers and the terms that could be in these polynomials. But we're just looking at vaguely, in general, some different properties that we can see with these polynomials and the equations themselves and how it relates to the x-intercepts and the turning points. So what I want you guys to do, and this is more so what you're going to be doing in my math lab, is you're going to be given an equation and you're going to have to list a graph of an equation, excuse me, and you're going to have to list the properties that you notice there. So what is the end behavior? Does that mean the degree is even or odd? Does that mean the coefficient is positive or negative? How many x-intercepts are there? How many turning points are there? So I want you to take a few minutes, see if you can look at these 6 sets of properties and match the equation that it is describing, or vice versa. Start with the graph of A and find the description that matches A. So take a few minutes and try that. Okay, so looking at number 1, we want it to be an even degree. So that tells me my ends are going to go in the same direction. Negative leading coefficient, meaning my ends are both going to go down. So looking at the 4 graphs or 6 graphs that I have here, there's only one graph where both ends are going down, and that is graph D. There are also 3 x-intercepts, 1, 2, 3. In the next one, you wanted an odd degree and a negative leading coefficient. So that would give me end behavior that would look like this. So on the left, going up. On the right, it's going down. And let's see here. I think, again, I only have one graph that matches that. This guy here. A, it also has 4 turning points. 1, 2, 3, 4. In number 3, I want an even degree. Get my pen back. There we go. A positive coefficient. So that means both of my ends are going to go up. So it's either C or B because both of my ends are going up. So we need that third property. It says the 0 of multiplicity 2 at x equals negative 3. So a 0 at x equals negative 3. And both of these graphs have a 0 or an x-intercept at negative 3. We want the one that has a multiplicity of 2, meaning it's even. And remember, even multiplicities turn around. So that narrows it down to graph C. Graph B has an odd multiplicity at negative 3 because it's going through the x-axis at that point. In the next one, we want an even degree function with 3 turning points, and all those turning points have y values less than or equal to 0. So even degree, I think I only have one even degree left, and it's B. And it has 3 turning points. All of those turning points have y values less than or equal to 0. So B. Finally, numbers 5 and 6. They're both odd degrees, so that doesn't help us any. Number 5 has a positive leading coefficient, and actually it looks like both of these have a positive leading coefficient because they're going down on the left and up on the right. Number 5 says we want 3 x-intercepts, each of multiplicity 1. So looks like each of them have 3 x-intercepts. But if you look at graph F, there are a couple places where we're turning around on the x-axis, which means the multiplicity is even. It can't be 1. It can't be odd. So that means this must be E. And then finally, the last one, we want an odd degree with 4 turning points. F, if I label them, there are actually 4 turning points here. 1, 2, 3, 4, and 3 x-intercepts, which we already said. So that's graph F. Okay, in the next problem, we're going to just review quickly how to find max and mins in your calculator. So go ahead and get your calculators out. We're going to do this with a cubic function. I know it's a cubic function because my highest degree is 3. We're going to find local max and mins. These are just your, again, general max and mins we found before for y equals x to the third minus 27x. So we're going to go to y equals. We're going to clear out the equations that are in there. And we're going to type it in x to the third minus 27x. And then I'm just going to graph in my standard window. Zoom 6 will do that for me. I definitely need to zoom out, though, a little bit here. So I'm just going to hit zoom out, number 3, and then enter. And then I can almost get a picture of it. It looks like it needs to be a little bit taller, and I could maybe narrow in my x-axis a little bit. So let's change our window. Let's make our x's. Let's just go back to -10 to 10. But I want my y's to be higher. I want my y's to be, oh, I don't know. Let's say -100 to +100. Okay, and this you'll have to play around with from one problem to the next. You could even zoom fit. Maybe when we're done with this problem, we'll hit zoom fit and see if that gives us a reasonable picture. My x's, maybe I'll count by 2's on my x-axis. My y's, maybe I'll count by 10's or 20's on my y-axis. That's how often I'll see a tick mark. So now if I hit graph, oh, there's a much better picture for me. Okay, so this is what we're looking for here. I want to be able to see those minimum and maximum values. And you can see on the left, I have a maximum, and on the right, I have a minimum. So what we're going to do is we're going to hit second, calculate. We're going to hit, doesn't matter which one we'll do first, we'll do maximum, number 4. And the maximum point is over to the left here. So you can either, I know we zoomed out a little bit, you can use your arrows to kind of be at that maximum and then just go to the left side of it. Or you can select what X value you think that is. But remember, we changed the scale a little bit, so that might be harder. So I'm just going to go to the left side of that maximum and hit enter. I'm going to go to the right side of that maximum, hit enter, and then hit enter again. And the maximum is at -354. I'll just drag that over. Let's repeat the process again. Second, calculate minimum, number 3. And I'll do the same thing. I'm just going to scroll over to where that minimum is located. On the left, I'll hit enter. And on the right, I'll hit enter and then enter one more time. And it looks like it gave me kind of a weird decimal here, but it's +3, -54 is that other value. Nope, come on, get over there. There it goes. All right, so those are the answers to part or question number 1, I guess here. So let me write those in. Let me pull my pen back up here. So I have a local maximum at the point -354, and I have a local minimum at the point 3, -54. Now, if we say absolute maximum or absolute minimum, that's just on a specific interval. So it's not meaning necessarily a turning point. And you definitely need to use your calculator for these. So this is saying if there's an where is the absolute maximum on the interval 0 to 3? So that means between the numbers 0 and 3 on this graph, what's the highest point there is? So again, not necessarily a turning point because we're just looking at part of the graph here, but it's the same procedure. We hit second, calculate. We're trying to find a maximum, so we select number 4. And it's telling us use the interval 0 and 3. So that means 0 is our left bound. I'm just going to hit 0, enter. 3 is our right bound. 3, enter. And then guess, hit enter one more time. And it tells me I've got these weird numbers with an E at the end of them. E in your calculator means scientific notation, times 10 to that power. So a number times 10 to the -6 or a number times 10 to the -5 is a super tiny decimal, which essentially means this rounds to 0, 0. Sometimes your calculator freaks out at 0, 0. So where is the absolute maximum between 0 and 3? It's at the coordinate. We just round if we see those E's, 0, 0. So anytime you see in the calculator some crazy number that you're like, wait, that's at the origin, but it's telling me it's 3 and -9, just look for the end of the number. If you see the E's, make them 0. Okay, our last 2 problems are application problems, and we're going to be using the calculator to help us here a little bit. If $4,000 is invested for 3 rates at a rate R compounded annually, so this is a compound interest formula, you might have seen this in a previous math class. The future value of this investment is given by S, or sometimes you'll use an A if you've done this in a previous class, equals, oops, that shouldn't be a 2,000. That should be a 4,000. 4,000, 1 plus R to the third, where R is the rate as a decimal. So for example, if my interest rate was 7%, my R would be 0.07. We want to find the future value of this investment at the following rates. If R is 0, 0.05, 0.10, etc., etc. This is just plugging numbers into this function. And this is a polynomial function. This is a cubic function because my highest power is a 3. To evaluate these, we're going to just go to our home screen. So I'm just going to hit second mode, which quits back to my home screen. And I'm going to start with the first one, 4,000. 1 plus, and the first R value we're asked to evaluate here is a 0. So an interest rate of 0 to the third power. And we get $4,000. So if I have no interest at all, I'm going to end up with, at the end of the year, end of 3 years, $4,000. I have exactly what I started with, so that should make sense. The next R value we needed to evaluate was 5%, 0.05. Again, to the third power. So that's going to give me quite a bit more money, $4,630.50. Now let's do the same thing. We can just continue in our calculator with the other rates, 10%, 15%, and 20%. And I'll show you a shortcut here. If you don't want to keep typing the whole thing in, you can just hit second, enter, and you can just change the number. So instead of 0.05, 0.10. Second, enter. Instead of 0.10, 0.15, enter. And I'm going to drag that over before I lose it. I don't want to lose any of those answers there. There we go. And let's get one more. The last one was 20%. So second, enter. I'll change my interest rate to 0.20. And there's the last one, 6,912. Okay, and then you could, of course, put those with the dollar sign. Instead of 0.5, you'd say 0.50. You round to the nearest penny, that sort of thing. Okay, so how much more money was earned at a rate of 20% than at a rate of 10%? So we need to look at how much we earned for both of those. At the 10% rate, we earned $5,324. And at the 20% rate, we had a total of $6,912. If we want to know how much more was earned than the other, we just find the difference. We're going to subtract. And you can use your calculator for that. 6,912. Do it on my calculator to the side here, minus 5,324. I get $1,588. Part C says, is 10% or 20% a more realistic rate? If you are ever asked this question, the lower interest rate is the answer. If you are investing something at a bank, for example, your interest rate is going to be more like a 0.01%. So 10%, 20%, these are extremely large numbers, something that you might get in like a mutual fund or a stock investment that's doing really well. But in general, the lower interest rate is always more realistic and reasonable. We want to graph this function on the following R values. Remember, R is our input, so we're going to think of these like our X values in our calculator. So I'm going to go to y equals, and I'm going to type in my equation. But again, R is our input, so I'm going to put X there instead. 4,000, 1 plus X to the third power. Okay. In my window, we're going to change some numbers. The X's we're supposed to use, or the R's, are between 0 and 0.24. And then the X scale, you can count by whatever you want. Maybe it will count by 0.1, something like that. The Y values, Y here represents the value of the investment. So we know the lowest value of the investment. It can't be a negative number. That wouldn't make sense here. So I'm just going to say 0. We really know that if it's an R value of 0, we're going to be at 4,000. 4,000 is going to be the lowest value we actually see on this graph. And if we're at 20%, we got all the way up to 6,912. So I think I'm going to make my X or my Y max a little bit bigger. I think I'm going to make it 10,000. and my y scale, I'm going to count by 1,000. And let's see if that gives me a good picture of this graph. And there we go. There is our function graphed between our values of 0 and 0.24. I'll make that a little bit bigger here. And I can label on my graph. So here is my R, 0 and 0.24. And then my Y's, remember we went from 0 to 10,000. So what we're seeing here, that's where the graph started at 4,000. And we can see how it's increasing based on how much our R value is increasing by, what our interest rate is. Okay, our very last problem is, again, a profit function. I know we've seen some of these before. This says the weekly revenue for a product is given by R of x equals 120x minus 0.015x squared, and the weekly cost is C of x equals 10,000. I'm going to put a little comma there so we remember that's a 10,000, plus 60x minus 0.03x squared plus a big number times x to the third, where x is the number of units produced and sold. So that's important. X is the number of units that are produced and sold. We want to know how many units will produce a maximum profit and what will that maximum be. So we're ultimately calculating a maximum here, but it's a maximum profit, which means we need a profit function. So we need to review very quickly what profit is. Profit functions are revenue, how much you bring in, minus cost, how much things cost you. And profit's kind of where those two things balance out. If your profit is positive, that means you're doing pretty good. So we need to calculate that profit function first. Revenue function is 120x minus 0.015x squared minus our cost function. Be careful here, the cost function must go in parentheses. 10,000 plus 60x minus 0.03x squared plus 0.401x to the third, if I can squeeze it in there. Okay. Then this is subtracting polynomials, which we did a few chapters ago. To do this, you remember that you need to distribute the negative in first, and then we're going to combine together like terms. So my profit function P of x is, bring down my 120x and my negative 0.015x squared. I'm going to change all of the signs in my cost function inside the parentheses there. So it's going to be a negative 10,000, a negative 60x, a positive 0.03x squared, and then a negative 0.401x to the third. Okay, so now we need to find the maximum on this function. So we're going to graph it in our calculator. Back to y equals 120x minus 0.015x squared minus 10,000. Scoot over there a little bit. Minus 60x plus 0.03x squared minus 0.12341x to the third. Now before I graph this, I want to make a note here that my leading term, the guy that has the highest exponent, is this guy at the end, x to the third power. So we know the degree is odd, and the leading coefficient, the number in front of it, is negative. So to see a full picture of this graph, we should expect that the ends are going up on the left and down on the right. So whatever we zoom, we want to make sure that we're seeing those ends happen. If I zoom in and I only see, like, I don't know, this part of the function, I'm missing something, and that maybe is where my maximum or my minimum is happening. So I don't want to do that. So just make sure that you can see at least those ends. So what we're going to do, I'm just going to hit zoom 6 and see what it looks like, just our standard window. And it doesn't look like that's giving me a whole lot of anything. So let's see if zoom fit, this is one that we've talked about before, maybe gives me a decent picture. And again, not really a great picture. So let's change our window here a little bit. And let's see what it gave me for a window. My x's right now are only negative 10 to 10. So maybe let's say like negative 100 to positive 100. Let's see what that does. Hit graph. Nope. So let's hit window. And let's see what's happening with our y's. Our y's are going from negative 10,000 to positive 10,000. You know what? Let's look at what these variables even stand for. X is a number of units. So could X even be a negative number? Absolutely not. Let's make it 0. And then Y represents our profit. Could Y be negative? Yes, but we're trying to find a maximum profit. So I'm going to assume that it's a positive number. So let's say 0 to, I don't know, 5,000. Just picking a number. We can always make it bigger later if we want. So let's hit graph there. See if that gives me a decent picture. Whole lot of nothing. Okay, so let's hit window again. Let's make my X 1,000. Graph it. Okay, we're getting closer here. Window. Let's make my X 5,000. Graph it. There we go. So we see it going up and back down again. But I need to see that maximum. So let's make our Y's much higher. Let's make them, I don't know, 20,000. Okay, we're getting there. Still way above. Window. Let's make our Y's 100,000. There we go. Okay, so I'm going to go back to that window. You can match mine. So again, my X's are the number of units. So I said 0, and then I just started making it bigger until I saw the graph. My Y's are my profit, which we want to find a maximum, a height. So I'm going to start with 0, and I picked 100,000 eventually to be able to see that maximum. Now, if I look back at that graph, we are seeing the ends happen here, but we're not concerned about the negative. We can almost finish this graph. On this side, it's going to do this, and on this side, it's going to go do this. So it's going to match those ends that we were talking about. All right, let's calculate that maximum and finish up this problem. So in my calculator, I'm going to hit second calculate, maximum number 4, and then I'm just going to do the same thing we did before. I'm just going to scroll to the left and the right of it. So, oop, I lost it. To the left, I hit enter. To the right, I hit enter, and then hit enter one more time. And you can see it's rounded kind of strangely there, but my maximum is occurring at 2,000 and 90,000 is that point. So what does my X stand for? My X is the number of units sold. So 2,000 units will result in the maximum profit. And my Y, 90,000, is the maximum profit that we can have from this function. Okay, so I know it's a little bit messy with the zooming and the window, and you're just going to have to play with that a little bit. It's going to be different for every problem, but the point of this lesson is you want to understand, you know, odd degrees and coefficients, positive and negative, even degrees, how that all relates to make sure you're seeing a full view of the picture. And I will tell you, a lot of the Math Excel, or excuse me, my Math Lab problems are going to